Well, welcome to lesson 7.5, looking at the sum and difference identities, continuing on in chapter 7 with trigonometry. This is our second last section. And the sum and difference identities are a little bit different than the previous ones in terms of how we make use of them. But as we begin, I would like you to take a look at these warm-up questions that you see here. And the question is, of these three, which are actually identities? And whether they're identities or not, can you find a value for A and a value for B that makes the equation true? So just a reminder here that an identity is an equation that's true for all values of the variable in the domain, whereas an equation may only be true for some of the values in the domain. So pause the video at this point and try these three questions. Find a value for A and B that makes the equation true, and then state whether the equation is an identity, yes or no. Well, let's look at number one. Suppose I pick a value like, let's say, A is equal to 2 and B is equal to -3. So if those are the values that I pick, then on the left side, I'll have 3 times 2 plus -3. And I want to see if that's going to equal 2. No, let's fix that. There we go. That should have been a 3 times 2 plus 3 times -3. Are the two sides equal? Well, let's see. If I think order of operations and I simplify this part, that gives me a -1 times the 3, which is -3. And on the right side, we'll have 3 times 2 is 6, minus 9 does give me -3. So I found a value for A and for B that makes this equation true. Is this an identity? Well, you probably recognize fairly quickly that yes, it is an identity. So I'm going to take this and I'm just going to throw this away for the moment. And we'll look at how do we know that this is an identity? Well, we could prove it, right? And as we've done proofs in the past, I could just work with each side of the equation separately, distributing the 3 in. I get 3a plus 3b. Oh, that's the distributive property. And it's equal to the right-hand side of the equation. So, yep, an identity. Number two. Well, suppose I picked the same values. Suppose I again said A is equal to 2 and B is equal to -3. And I look at the left side, 2 plus -3. And then I'm going to square all that. And then 2 squared plus -3 squared, and evaluate each side. So here I'll have a -1 squared is 1. Here I'll have a 4 plus 9. 1 does not equal 13. So that's enough to tell me this is not an identity. Because as I look at the equation that we have, there are no implied restrictions on what A and B can be. So they could be any real number. So that one, not an identity. Well, that's all leading us up here to number 3. Number 3, is this an identity? Well, let's begin again by choosing some values for A and B. So let's say that A is equal to 30 degrees and B is equal to 60 degrees. So then I'll have the sine of 30 degrees plus 60 degrees. And is that equal to the sine of 30 degrees plus the sine of 60 degrees? Well, on the left side here, we can see that if I simplify, I'll get the sine of 90 degrees, which the sine of 90 degrees is equal to 1. And the sine of 30 degrees is 1/2. The sine of 60 degrees is √3 over 2. 1 plus root 3 over the common denominator of 2. These two sides are not equal. This is not an identity. Because again, A and B have no restrictions on the values they can have because the sign of A is defined for all real numbers, similarly for the sign of B. Could we find numbers that would work? Well, we could. Suppose instead I picked for my A value and I said, well, I'm going to go with 30 degrees because I like 30 degrees. And for my B value, I'm going to say, well, what if I had 0 degrees? So then my equation would look like this. So on the left-hand side, I would just have the sine of 30 degrees. And on the right side, sine of 30 degrees. I'll just rewrite it. And the sine of 0 degrees. Well, the sine of 30 is a half. Sine of 30 is a half. Sine of 0 is 0. In this case, it works. So there is a solution to this equation, but it's only for this one pair of values. We could probably find other pairs too, but works in this case, but it's not an identity. We could have done something similar in question number 2. If either A or B was 0, then we could have gotten an equation with a solution. But that leads us to the sum and difference identities. So you'll notice here in this equation that we just looked at, what we might be tempted to do would be to distribute this sign into the brackets of A and B. But we can't do that. Just like if I had something like the square root of A plus B, like this, that's not equal to the square root of A plus the square root of B, right? If I did the square root of 9 plus 16, square root of 9, square root of 16. Well, I'm running out of space here, but the square root of 9 plus 16 is the square root of 25. So on the left side, I'm getting a 5. On the right side, I have the square root of 9, which is 3, and the square root of 16, which is 4, which adds up to 7. My right side and my left side are not equal. The two sides are not equal to each other. So I can't just distribute that square root sign in because it's not being multiplied. And similar here, this sign is not being multiplied to the A and the B. It's an operation on the A and the B. So here in the table below, you can see the 6 sum and difference identities. And we're not going to prove them, but we'll just show you how we can make use of them. In this first example, number 4, we want to find the cosine of 75 degrees exactly. Now, 75 degrees is not an angle that well, it's not a special angle. It doesn't show up on the unit circle or in special triangles. So what we would do is we would look at the 75 and we'd ask ourselves the question, what special angles do add up or subtract to 75 degrees? And then we would rewrite the question. So I could say, well, let's see, 75 degrees is the same as 30 degrees plus 45 degrees. Both of these are special angles. So I could find the value of cos 30 or of cos 45. But I can't just find the value of each of them separately. I have to look at this and say I have a cosine function and I'm adding. So I want to look at this identity here, and I'm going to rewrite the identity. So this will equal the cosine of the first term, which is 30 degrees, times the cosine of the second term, 45 degrees. minus the sine of the first term, 30 degrees, times the sine of the second term, 45 degrees. And each of these trig ratios we can discover as exact values. We can use the unit circle or special triangles. We've done enough of that so that hopefully you would get that this is root 3 over 2. And the cosine of 45, if we use the unit circle, we get root 2 over 2. Sine of 30 is 1/2. And sine of 45, also root 2 over 2. And then we would simplify this collecting the like terms. So root 3 times root 2 is root 6, all over 4. And we'll subtract root 2 all over 4 to get an answer of root 6 minus root 2 all over that common denominator of 4. So we figured out an exact value for the cosine of 75 degrees. And that's one way that we make use of the sum and difference identities. Let's look at a similar question, but we'll do this one in radians instead of in degrees. Radians can be a little bit trickier because once again, we're going to ask that same question, what special angles add or subtract to pi by 12? But with fractions, it's not so easy. Now, again, you may want to switch to degrees and do it in degrees, but if the question is given in radians, you are expected to show all the steps in radians. So, what could we do? Well, we could think about adding or subtracting, and in this case, we'll subtract because pi by 12 is fairly small, but I'm looking for two numbers that have a common denominator of 12. They both have a pi in the numerator. So I have so many pi's by 12 minus so many pi's by 12. But I want it to be reducible because all of the special angles either have a 1, a 2, a 3, a 4, or a 6 in the denominator. Those are all factors of 12. So I'm going to look at what factors of 12 subtract to give me 1. Well, here's one possibility, 4 and 3. 4 pi by 12 minus 3 pi by 12 will give me a pi by 12. The value of choosing these numbers is that 4 and 12 have common factors, so they can be reduced. And I can reduce it to a pi by 3. Similarly, the 3 pi by 12 I can reduce to a pi by 4. So there are only some values that will work. So I could have thought, well, what if I did 5 pi by 12 minus 4 pi by 12? Well, that'll reduce to give me a pi by 12, 1 pi by 12. And this 4 pi by 12 I can reduce to get a pi by 3, but this 5 pi by 12 I can't reduce. So I can't find an exact value of any trig function that has a 5 pi by 12 as its argument. So I don't want to use that. That's why we're using something like over here, the 4 pi by 12 and 3 pi by 12. So then we need to remember what is the identity. It was on the previous page, also on your formula sheet. It will look like this, where we take the sine of our first angle times the cosine of the second, and then we'll subtract cosine of the first angle times sine of the second angle. Well, sine pi by 3 is root 3 over 2. Cosine, this time I did it using the special triangles. So the cosine of pi by 4 would be 1 over root 2. And then similarly for cosine pi by 3 and sine pi by 4. And then we would just simplify our answer. So we could leave it as I have here in the box. Again, we're not always picky about whether we leave radicals in the denominator or not. Or we could simplify it so that we rationalize the denominator. And the way we would do that, if you'll recall from grade 11, we would take this denominator, we want to multiply it by the square root of 2. And if we do it in the denominator, we do it in the numerator as well. And when we distribute this root 2 into the numerator, that's where we get the root 6 and the minus root 2. So there's one way we can use sum and difference identities. Here's another example. And really this one's playing around. We're given this, we want to figure out, well, what identity is this equivalent to? So I look at my formula sheet and I see, oh, there's a sine alpha cos beta minus cos alpha sine beta. Well, that's the same identity that we used in question number 5, which is just the sine of alpha minus beta. So there's the identity from the formula sheet, and then we can just replace the alpha and the beta with the 8x and the 3x, simplify it down, and this is equivalent to the sine of 5x. All right, question number 7. Similar, we want to look and see, can we find this as an identity on the formula sheet? So I look at the identities and I observe, oh yeah, so I have a addition on the top and subtraction in the denominator. That wasn't supposed to look like that, but anyhow, let's look ahead at the question again. So that will be, select this, that'll be the sum of two angles in a tangent function. And in order to add those together, I'll want to get a common denominator. So the pi by 6, I'll multiply numerator and denominator by 2 to get a 2 pi by 12. Add together, and I get the tangent of 3 pi by 12, which again, we can reduce to a pi by 4. And so we get tangent of pi by 4 is equal to 1. All right, now that we've done a few examples, I'd like you to take a look in your workbook at page 642 and try question 4a. So you can pause the video while you try those questions, that question. Well, here's the question. Cosine of an angle, cosine of an angle. I want to see where is that in my identities. So here, cos A alpha times cos beta, there's a cos alpha times cos beta. When we look here, I have addition, and so it's actually going to be subtraction of the two angles. So that's how that identity works, and we can subtract the 8 theta minus 2 theta to give us 6 theta. Next example. We have an angle alpha in standard position, terminal arm in quadrant 3, and we know the value of cosine. We have an angle beta in standard position, its terminal arm is in quadrant 2, and we know the value of sine of beta. We want to find the exact value of sine alpha plus beta. So we look at our identities and we see, well, sine alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. So what do I know so far? Well, in this question, here I had cosine of alpha, so I know cosine of alpha. I have the sine of beta, I know the sine of beta. I don't know the value of these two trig functions. And so that's what I need to figure out. So what I'll do is I will sketch my angles in standard position. So here I've sketched the angle alpha. And because I know the cosine of alpha, and I remember cosine is x over r, I'm able to fill in those two sides of the triangle for the angle in standard position. Pause the video if you need time to write more of this down, but I'll continue. Once I have two sides in this right triangle, I can use Pythagorean theorem to figure out the third side. And I just remembered that Pythagorean triple, the 3, 4, 5 right triangle. But again, you could do x squared, so negative 3 squared plus y squared equals 5 squared, and then solve to get the y value. When you take a square root to get the y, you'd get a positive or negative 4, but because we're in quadrant 3, this has to be a negative 4. Well, if I know that y value, I know the value of sine of alpha. So this is no longer a mystery. I have figured out the sine of alpha. Why don't you pause the video for a moment and sketch the angle beta in standard position and determine the value of cos beta. Here I have my angle sketched in standard position. Sine of beta is y over r, so I know the y value and the r value. And again, the question told me beta was in the second quadrant, so I knew where to draw it. Pythagorean theorem will tell me that third side. So this time I've shown the process where I did the r squared minus y squared to give me the x squared. And again, because I'm in quadrant 2, I know my x value has to be a negative. So I've chosen the negative square root. And once I know x, I know cosine of beta is negative 2 root 2 over 3, because up here my r value was 3. So now I know everything I need for completing this question. Sine of alpha, negative 4/5 from our first diagram, cosine of beta from our second diagram, and then the information given in the question. And then we'll just simplify to get this as our final answer. Again, feel free to pause the video if you need to. When you're ready to move on, there's another check your understanding question I'd like you to do. So from the workbook, page 644, question number 8a, Roman numeral 2. So this will be the next question. I'll have you work on, pause the video, work through the question, and then restart the video. Well, you should have finished this question and checked your answer, so I will go through it relatively quickly. First of all, I think about what is the identity. So cosine of alpha minus beta, here I have the right side of the identity. And what do I know? Well, I know cosine of alpha is 2/5, and the sine of beta is negative 1/3. So again, there are two trig functions that I don't know, I need to figure out. The angle alpha, let's see, standard position in quadrant 4. See, is this alpha? It is. There we go, quadrant 4. There's my angle. And the information I know, since I know cosine, I know x over r. So the x is 2, the r is 5, and I can use Pythagorean theorem to figure out the y value. Again, I chose the negative for the y value because I'm in the fourth quadrant. And I figure out sine of alpha, negative root 21 over 5. Then as we look at the angle beta in standard position, there I have it drawn. Again, the question told me it was in quadrant 3, so I knew where to draw my terminal arm. I know that sine is negative, and so as I fill in my information, my y value is negative, and my r value always positive. And I use Pythagorean theorem to figure out what is the x value. Again, in the third quadrant, x will be negative, so I chose only the negative square root. And that gave me the value of cosine of beta. And so I could substitute all of those in the cosine of beta, negative 2 root 2 over 3, sine of alpha, negative root 21 over 5, and then simplify to get this as my final answer. Let's move on. So let's look at another proof. We want to prove this identity. Again, I can see that I have the sign of a subtraction of two angles. So I think about my identity sheet and the sign of alpha minus beta. What is that equal to? So I will get this sine of alpha cos beta minus cos alpha sine beta. But instead of alpha and beta, I have a pi and an x. Well, this time is a little bit different because I have a pi in here. Remember, pi is not a variable, so I can evaluate the sine of pi, and that's just equal to 0. Cosine of pi is -1, so I can replace values in for each of those trig statements. 0 times cos will be 0, and subtracting the -1 times sine just gives me the sine of x, and the left side is equal to the right side. As you need, again, pause the video, but I will continue on. And here we have the last question for this lesson. Once again, we have an equation solving question. But as I look at this left side, hopefully you're recognizing that this looks like one of the identities. Cosine, cosine, that's a hint that it's going to be a sum or difference identity for cosine. And I just need to look on the formula sheet to figure out which one it is. So here I discover it's the difference identity. And what you'll notice as you're working with the sum and difference identities for cosine, if this is addition, this is subtraction. For sine, that's not the case. For sine, if I have addition of angles here, I'll have addition of angles on the right side of my identity as well. But in this case, it's cosine. So I subtract, I get cos 3x is equal to 1. As I mentioned before, this type of question we will only solve by graphing. So up to this point, we've done all the algebra we need to, and we can just sketch a graph to find the solutions. So here we look at the domain from 0 to 2 pi. Include 0, don't include 2 pi. So as I go through here and I graphed, the left side is the cosine function, the right side is y equals 1, and I can see these 4 solutions. But again, keep in mind the domain that we had means that we are going to reject the 2 pi because that's outside the domain. So x was less than but not equal to 2 pi. So we have these 3 solutions for this question. And there we go. That finishes off this section 7.5. And we have some practice questions listed at the bottom of the page. So have fun working on those. Make sure you highlight questions that you have so that when we gather together, you can ask those questions of me. Alrighty, have a good day.